let's start. Transform data. Why we transform data? Because we are not interested in few features of the data, maybe. So, -2, -1, 0, 2, 3. This is x, and maybe I choose the easiest possible values for these. And I'm interested in a new random variable that captures only the absolute value, the magnitude of the random variable. So I don't care about the sign, I just care about the absolute value, the magnitude. But then, what are the possible values of y? Of course, I cannot see negative values, 0, 1, 2, 3. The question is how to get the probabilities. I don't want to go back each time to x, but that's the way, I just need to do it once. So what is the probability at y is equal to 0? Well, this is the probability at absolute value of x is equal to 0, because that's what y is. And this is equal to the probability at x itself is equal to 0, which is 1/5. And good news, I can fill this question mark here. Okay, this was easy. Also, the next step is easy. It requires, it encodes the complexity of the problem somehow. The probability at y is equal to 1. Well, now I do have two options. That's the thing. Either x is equal to -1, because absolute value of -1 is 1, or x is equal to 1. Notice that I'm jumping one step here. I'm skipping one step, because these are two disjoint events. They cannot happen at the same time. So I'm using the third axiom of the probability. Well, a version of it with finite many events. And now I do get that the probability of these is 1/3 for obvious reasons. No, it's not. It's 2/5. Whenever you read a paper, if you want to find a mistake, it's exactly in the spot where it says it's easy to see or trivial. In this case, this was a mistake, so it's 2/5 there. Okay? Same thing happens with 2, because there are two ways to get it, and these probabilities were all equal to each other. No, it's not clear. It's wrong what I wrote. No, it's wrong. Again, I should have got some coffee. There is only one way to get 1, and this way is through. So there is only one way to get 1, and it's through -1. So the answer here is still 1/5. Okay? So there is only one way to get 1. There is the probability to get 2 has two options. And this is finally 2/5. And of course, this is 1/5. So let me summarize. If you're interested in the absolute value, 2 is the problem here, and it's easy to solve. You just take the sum of those probabilities. Now, this is an easy problem, but the way we have to formalize it, it's complicated. We do it in abstract now for a general function g, okay? And if you have a general function g, this formula is telling you whenever there is ambiguity of where you start, so it's the case of 2. There was ambiguity because you could start from two different values of x and get to the same value of y. Whenever there is ambiguity, you sum over the values of x. That gives you the same outcome. So those inputs, that gives you the same output. You sum over those probabilities. It's clear? Okay. Let's work this example here. Well, this one, it's nice. Let's start with this, actually. Let x be a binomial random variable with parameters n and p. Now, what's the meaning of a binomial? Where is used? Binomial NP. How do I interpret it? Yes?
It's the number of trials and P is the probability of success.
Exactly. But what does it count? Those are the parameters. The random variable itself is used to count, in the scenario that you described, is used to count what? Number of successes. Okay, so x is the number of successes. Out of the n trials that are all the same type of trial, independent of each other. Now, if I take the number of successes and I subtract it from x, from n, what is this random variable? What should be? What I'm counting. First, what I'm counting here. So, number of failures. So this is the number of failures. Okay? But these are labels that I put for what is for me a success, maybe for you is a failure, or vice versa. Right? These are labels that we use. We are counting in a dichotomic way. We are distinguishing between A and B. I can call it failure or success. What's the distribution of this? What's the probability of a failure?
It's 1 minus the probability
Of failure. So 1 minus P. How many trials do I have? N. So what's the distribution of the number of failures?
1 minus the binomial.
Yeah, so it's binomial n 1 minus p. So it's like I have n trials, I count the failures, each has probability 1 minus p. So it's binomial n 1 minus p. This is the answer. Now, this is a different approach from what I described above. Above there is a way to see it, right? So let's use the approach above. Let's see how it works. Here I got an answer using more than intuition. This is rigorous somehow, I think. But before you start any computation, my point is get the answer in your mind. If what you get through the computation matches, usually it's okay. It's not a proof, but it's okay. If you have a proof, it means that there is no mistake there. If what you compute differs from what you have in mind, either it's very nice, you created a kind of paradox, something that conflicts against your intuition, or there is a mistake in your computation. Usually it's the second. Now, let's try. N minus x, this is my y. What's the probability that y is equal, sorry. Let's start from the genesis. What are the possible values of y? Don't need to raise your hand. We are... Exactly. I can have 0 failures if x is n, all successes. Or 1 failure if x is n minus 1. But in any case, if I have n trials, I cannot have a negative number of failures, or I cannot exceed n. So these, the possible values, is my handwriting okay? Can you read? Possible values of y are 0, 1, 2, up to n. Are we good? These are the possible values. What I'm left with is to compute the probabilities of these values. So I don't want to enumerate each of them because we don't have time here. So let's be lazy, and when we are lazy, we have to use some kind of abstraction. Y equal to k. How do I translate in terms of x? If the number of failures is equal to k, what is the number of successes? N minus k. N minus k. So number of trials, n trials. We have that the number of failure plus the number of success is equal to 1, because there are no other options, and they are disjoint somehow, right? You cannot be both. Are we good? So if I ask for this to be the number of failures, it's the same as asking for x to be equal to n minus k, for this equation that I have at the bottom. Now I know how to make a computation. What is it? Just remind me what is the probability mass function of a binomial. So instead of k, I place this argument here, okay? Then p n minus k and 1 minus p to the power k. Hopefully my handwriting is clear here. Because I ask n minus k successes, so p to the power number of successes, 1 minus p number of failures. It's clear? Now, one nice and underestimated property of the binomial coefficient, these brackets here at the beginning, is that in general, this is general, n choose k is equal, I put some space here so I prove it, to n choose n minus k. Why is this true? Because by definition, look at what happens. This is n factorial, k factorial, n minus k factorial. If you swap these two at the denominator, you get the same thing because the product commutes, and k can be written as n minus k minus n, n minus k in brackets. So you will see, just do the math. Are we good? Let's summarize this, and let me summarize it by using a different color. So this expression here, I'll rewrite it here. I use what I just discovered, that n choose n minus k is n choose k. And I just swap those things. And this is exactly PMF of binomial with parameter, bless you, n and 1 minus p. Questions? Let me work this example as well. Before I move to this new example, do you have any question about the previous one? How is it going with the unit? Am I going too fast? How do you find the assignment? Today, I will give some, not hints, some tools to be used in the assignment. I'll remind you, you still have a bit of time, but it's good if you start in good shape. I'll try. Do you think it will create confusion if I post also assignment 2? How many of you want assignment 2 posted now? With, of course, a deadline well later, the deadline that I advertised in the Moodle already. How many of you want to see it now, this week? One. Why you don't want to see it? You want to suss mystery, okay. I mean, send me an email if you want to see it this week. I need to be sure that there is no confusion. I don't want people to submit assignment 2. Actually, yeah, let's wait next week. I take it back because the communication is not working properly for some reason. There are many people not reading my emails, and if I post it on Moodle, I know because the homework is not yet clear to everybody. I still receive a lot of emails about, misunderstanding in the homework. So I'll do it at exactly the deadline of the assignment 1. I'll post assignment 2. Okay, let's work this example and let's move on. So X is discrete uniform. Let's understand the possible values. What are the probabilities? Uniform distribution in many ways means just you give the equal probability to each item. So count how many do you have there. Yes? 1 over 2n plus 1. Perfect. So each of them, I'm not going to write all of them. 1 over 2n plus 1. 1 over 2n plus 1, and so forth. Now, let y be the absolute value of x. There is no narrative here. I'm not telling you why, you're just interested in the magnitude. Suppose it's interesting. And tell me the distribution, the PMF. So when I say distribution, with what we saw so far in the discrete, I mean probability mass function. In measure theory, distribution is something way more sophisticated. So, what are the possible values of y? 0, 1, to n. What are the probabilities?
0 will still be 1 over 2 minus 1, but everything else will be 2 over 2 minus 1.
Exactly. Why is this so?
Because in the as absolute value, everything has a negative.
Exactly, with the exception of 0. Yeah, thanks. So, any question? I think I'll put you a bit asleep if I continue with this pace. Let's move to expected value. Expected value. It's what we use frequently to summarize data. And it's a powerful way to summarize data because it's immediate. When you are asked, how is it going with your studies? You might say, okay, You can spell out the outcome of each exam, or you can simply provide an average mark. I would prefer the second. Of course, you lose data from the distribution. Expected value doesn't tell you a lot of things. And we are going to give more measures later, give more details. But the expected value is by itself very powerful. What is the definition? The definition is this one. It's very neat. You take the possible values, you multiply by the weight. What is the weight? The PMF at that value, the probability mass function, the probability of observing that value, and then you sum over all possibilities. With your exams, maybe what you do is you give equal weight, you use the uniform distribution to each of the exams, and just add up. Of course, there will be a correction at the end. We're not talking about it. Is this definition clear? We're going to see so many examples. Actually, with this definition, I want to start with an example. Look at the bottom of the page. Bernoulli random variable. So it only takes values 0 and 1. These are the possible values. 1 has probability P to be observed. What's the expected value? The expected value of X is equal to one possible value times P, which is the probability to observe 1, plus 0 times whatever times is, doesn't matter, but I'm going to write it, 1 minus P, which is the probability of observing 0. And of course, 0 annihilates the 1 minus P. The outcome will be P itself. Are we good? Now, suppose that each, so you tell me the average of your exams, of your marks, and you tell me it's -1. Would you believe it? I got a negative mark in my life, in high school. But in general, I do not believe on negative marks being there, at least not here. Okay? So I would not believe if you see an expected value that is outside the range of values. So you cannot see, if your marks are all positive, you cannot see -1 as an outcome. On the other hand, if 100 is the maximum value that you can get in each exam, I don't believe I can see 110 as an average. So if X is larger than C, and you're sure about it, then the expected value of X is larger than C as well. Now, I also a strong believer of proofs. How you prove this? In the context of finite random variable. How do you prove it? So what we have in our hands now, as this is a fresh concept, is just a definition. Now, don't take me wrong. Most of the time, mathematicians go back to the definition to get something done. So but in this case, we have nothing else. So we are forced to go there. The definition is what you see framed in red there. Sum over X of X, the probability mass function. Now, the information is that all the possible values of capital X are larger than C, all of them. So when I'm summing over, how do you relate this and this? What I'm saying is that all the small x are larger than c. Is it clear? That's the assumption. So this is larger than this. It's a comparison for each term in the sum. Serena? Let's have an example. 2, 3, 5, each with probability 1/3, 1/3, 1/3. My claim is that x is larger than 1, in the sense that all the values there are larger than 1. All the possible values are larger than 1. Now, when I take the expected value, 2 times 1/3 plus 3 times 1/3 plus 5 times 1/3, is it true that these are larger than 1/3 plus 1/3 plus 1/3? Yes, because I compare 2 with 1, and 2 is larger than 1. 3 with 1, 3 is larger than 1, and so forth. Now, instead of working with the example, I can do it in abstract and compare one by one. Are we good? It's clear? Can I delete the example? It's a bit messy here otherwise, okay? So I delete this example. And this becomes equal to C, because I can pull out from the sum over x, px. This is the PMF, so I should make it an effort to, this is the random variable, or these are the possible values. Okay? If this confuses you, I can remove this from the distribution. For the moment, we don't need it. This is the PMF of x. Are we good? But then what is this sum? Just 1, so this is equal to C, and I add a proof. It's 1 because of the properties of the probability mass function. You add up all the probabilities, you get 1. If you add up all of them, you get 1. C, so we start with an assumption. If x is larger than C, you could choose anything as long as this is true. So if this is true, this other thing is true. If that is true for some choice of C, then the expected value of x is larger than C for the same choice of C. So before, in the example, I chose C equal to 1. I could have chosen C equal to 1.5, so there is no unique choice. But if this is true, then this other thing is true. This is an example. Yeah. What other C can you choose there? Two, it's tricky because the strict inequality is not true. There is one value that matches your 2. 1.999 would do. So these, I managed to confuse you on something that is trivial, because the expected value cannot go beyond the maximum and the minimum value that you can observe. Are we good? The next is what you need for the assignment. The expected value is not really this one. Let me see if it's a bit tricky. I need something extra. It's the same principle. The expected value is linear. This allows you to do what? What does it mean, linear? It means that if you take the expected value of ax plus b, This is equal to A times the expected value of X plus B. Sorry. I'll give you another version of this, which is stronger and fits the assignment. Notice that this is trivial. You can prove it. It's easy. It just comes from the linearity of the sum. Sum is linear in the same way, and that the expected value is a sum. So. In this second part, B, you use the fact that the sum of the probabilities is equal to 1. That's not an issue. But what is telling you between the lines is you are looking at the expected value of this linear transformation of X. If you go back to the formula above, if you want to use the definition, you need to compute the probability mass function of AX plus B. And that is a lot of work. With the linear transformation, it's not too much. But with other transformations, it is. But even linear transformation, if it is complicated, see, I'll show you in a minute. On the other hand, this formula takes away all the problems because it tells you that you just need to know the expected value of X. You don't need to compute the probability mass function. You don't need to know the experiment of AX plus B. For AX plus B, it's complicated to find the PMF sometimes. I mean, it's not, but let me show you another case that is more complicated. So we look into the future, and I show you something else. Sum up to n of AI, xi. So you do not have one experiment, but you have plenty. Now, linearity can be pushed. And this is very difficult to get a distribution of that. But look what happens. This becomes sum of AI, expected value of xi. I will never, so I didn't prove this as I did not prove the other. I'm going to prove this, but you have to be patient a bit. I don't want to do it today. But what I want to do today is to show how powerful is this. First, are we good? Is this clear? Expected value is linear. To find the probability mass function on the left is difficult, can be impossible sometimes. But this formula tells you that you don't need to. And that's a basic principle. So you lose information with the expected value. It comes with a benefit. The benefit is that many times you do not need the probability mass function to compute the expected value if the probability mass function is derived from somewhere else. This is what you need in the assignment if you want to simplify your life. Are we good? So in MTH2225, we did have a nice problem. So it's called the hat problems, but we can choose another narrative. Suppose that we all came with a hat, so we are 9 people here. And so 9 people, it's already a lot. Oh, we all came with, let's make it the umbrella problem. Today is not raining, but we all came with umbrella. Suppose it's raining outside. We place our umbrella here, and then we randomly give umbrella to each person. So what's the expected value of people that gets their own umbrella right? If I give it randomly, I can give you her umbrella and all selected. The expected number of right, so X is the number of right allocations. By one right allocation means that I got my own umbrella and not Stephanie one's, for example. Is it true? Yep. least I want to be sure that the problem is clear. It's clear? Perfect. For you, it's boring, I guess. You can switch off now. So I want to compute x, the probability mass function, is a lot of work. And if instead of 9 I put 900, it's a lot of work. The larger the number, and after a certain threshold, you cannot compute the probability mass function. But the answer is very easy. x1 is equal to 1 if Serena gets her own umbrella. So what is the probability that Serena gets her own umbrella? 1/9. And is equal to 0 otherwise. We do the second person and so forth. Now, if for the second person, Stephanie, for example, if I do not consider what happened with the first experiment, she has the same probability of getting her own umbrella. I'm just asking one question without relating to the others. It's the probability that Stephanie gets her own umbrella. So 1/9 and 0. And each of us has the same chances of getting that umbrella. If I do not consider what happens, these random variables affect each other. I don't want to enter that. I don't want to. But the formula above doesn't assume any independence at all. It's clear? Good. What is x in terms of this? How do you relate x and xi? So each of the xi is Bernoulli, but how x, the random variable that I'm interested in, relates to the xi? That's the key. Exactly. You sum them. x1 plus x2 plus x9. What's the meaning of this? Each of them give contribution either 0 or 1 to the sum. If the first experiment is a success, gives contribution 1. So if it is a failure, gives contribution 0. So what is this sum doing? Counting the number of, the total number of happy people here that got their own umbrella. So this is x. No replacement. I'm just reallocating the umbrella. These variables are very dependent of each other, whatever that means. Let me give an example. If the first 8 people got their own umbrella, what's the probability that the 9th person gets his own umbrella? It's 100, it's probability 1, right? So they depend. But what I wrote at the top, which you cannot see, the property of the expected value, comes with no assumption about the dependence structure. And I'm looking into the future now to give you a tool well in advance for the assignment. Okay? So that's why I'm talking things that are not so clear now. What is the dependence? Are they independent? I did not talk about those things yet. But I think this formula, it's clear by itself. It's general, anything, in any context. I don't prove it now because I only consider one experiment at a time, so I'm just looking at x. Yep. So if I want to look at the expected value of x, this is the expected value of this. Linearity, This is the sum up to 9 of expected value of each of them. What's the expected value of one of them? We just, as you say, xi is Bernoulli. We computed it. What's the expected value? Well, the expected of xi, one step at a time. The expected value of a Bernoulli is 1/9, p. We computed in the previous page. So this is 9/9, which is equal to 1. Notice that if we were 10 people, the expected value will still be 1. If we were 100 people, 1. You would think that more people here, more success you would have. But there is a natural compensation that this computation makes clear, that if you increase the number of trials, you are happy, you have more trials, but you decrease in the same way the probability of success. And they compensate beautifully. We had a discussion on Poisson approximation about this, but this goes beyond. After our discussion, I thought this would fit this lecture, and I do repeat, if this is not clear, just be patient. I had 2 targets here, to show you how useful is linearity, and 2, you have some urgency here because you have an assignment, and this would make your life much simpler. So I deviated a little bit from the notes, but now I'm ready to go back, unless you have any question about it.
One is the fact that one is successive, so it's 1/9 is the probability that I'll get my outcome.
Exactly. It's 1/9. How to compute that? There is something to do, because the way combinatorialists would do is, okay, let's count the number of, you have 9 factorial possibilities to permute these umbrellas, but 8 factorial at the top are the only permutation that allow you to have your own umbrella. Or you can use a much simpler argument for that. I hope I did not confuse you or demotivate you. This is difficult, but I find this fascinating enough to be presented now. Now, I'm trying to scare you a bit. We have to compute the expected value of a binomial. We have to compute the expected value of geometric. We have to compute the expected value of Poisson. It's our task for this lecture is almost gone, but on Friday we savagely compute all these things. In order to do that, we need to have some formulas here. The second formula, I need to derive the second formula down. So we already know the very top left formula. I proved it for you. It's the binomial identity. Are we good? Now I'm going to prove the other formula, the one on the right. Notice that the third formula is not related to the expected. It's useful. We are going to prove it later. This one, you wait, because we're not going to use it now. Let me start with this. So I'll just focus on this good-looking formula here. How to prove this? Notice that the sum starts from 1, but doesn't really matter, because if you have a 0 there, 0 times something is 0. So let's do this. So sum over k, going from 1 to n, of k n factorial divided by k factorial n minus k factorial, a to the power k, b to the power n minus k. Strategy. Mathematicians go back to what they know. So here, it really shouts for apply the first identity, the one that we already proved. Apply the binomial identity. How? The second thing that I need to observe is these and these are related. K factorial is k times k minus 1 factorial. Are we good? So I can write k factorial. The definition is k times k minus 1 times k minus 2 and so forth. But this one is k minus 1 factorial, right? This is why I start with k equal to 1. So there is a partial simplification. This k here can be simplified with this k. And this becomes sum from k going from 1 to n of n factorial divided by k minus 1 factorial, n minus k factorial, a to the power k, b to the power n minus k. Are we good? Is this clear to everyone? The simplification there? Next step. Well, I would like to have a binomial coefficient there. How do I achieve that very quickly? As I'm running out of time somehow. Say it again. I missed one step. Start from the beginning, though. So you write k factorial as?
Yes, so if we write k factorial, so instead of k minus 1 factorial, we write k on k factorial.
But then you go back to the original equation. There is a subtle way to do it. I write n differently. I can write now, look, the numerator, it's okay, right? I use the same trick described above. The denominator, I'm writing n minus k as n minus 1 minus k minus 1, everything factorial. Do you agree that this is the same as above? As above. N minus k can be written in that way. Minus 1 plus 1. And then a to the power k, b n minus k. Now, the difference with the k, and the difference between n and k is that I'm not summing over n, I'm summing over k. N is constant here with respect to k. It doesn't matter the index. You can write k differently. You can use j instead. But n instead is a parameter here. It's fixed. You can pull it out of the sum. N minus 1, choose k minus 1. This is nothing else than that. A to the power k, b to the power n minus k. Now I'm over time, so I stop